Okay, welcome everyone to the June edition of the Ice Giant System Seminar Series. We have today Dr. Susan Benecchi from PSI. So I just want to remind you that if you are just joining us for the first time, the Ice Giant System Seminar Series, you can go to the link that I'll drop here in the chat and sign up for the listserv that gives you information on upcoming seminars, as well as you can view recordings of previous presentations as well, including this one, which we will get up onto the website a week or two afterward. Susan will present her talk, then we'll have some time for Q&A at the end, and then at the very end, we'll have a little bit of community news updates for job postings and upcoming meetings. So on that note, Dr. Susan Benecchi has had a passion for studying astronomy since meeting Clyde Tombaugh in elementary school. She studied at the University of Arizona for her undergraduate degrees in astronomy, physics, and religious studies. Her graduate work at MIT focused on discovery and characterization of Kuiper belt objects, inclusive of color, light curve, and binary properties. She continues this work today using a combination of ground-based telescopes, HST and JWST. She is also a co-I on New Horizons, being part of the Arith-Koth discovery team and continuing the search for additional KBOs to be observed by the spacecraft. She is also active in astronomy and education. And today she is here to talk to us about the Kuiper belt binary and color context of the outer solar system. Go ahead and take it away.
Okay, thank you. Thank you for coming. Thank you for listening. I'm going to present today on some work that's been ongoing for way too long. It kind of got delayed in some of the pandemic, and so the paper has been sort of sitting, and it should come out by the end of the year. But we've been looking sort of at from the discovery of KBOs in general, and then specifically focusing on smaller and smaller populations, subpopulations, since there are many more objects known now than when I started this particular work. So I feel very privileged in the sense that I came into the study of KBOs about the time that they were discovered, working with as an undergraduate at the University of Arizona with Don McCarthy. And I see Larry Lebowski is on as well. He was my original mentor as a high school student. So this goes a long ways back. And there's been a lot of work that's been accomplished over the last 30 years, which is really exciting. My collaborators in this effort are Alex Parker, who's now at the SETI Institute. He's doing a lot more sort of spacecraft work. Simon Porter at Southwest Research, Michelle Bannister at the University of Canterbury in New Zealand, Will Grundy at Lowell, Keith Knoll, who was my postdoc advisor at Space Telescope, but he's now at Goddard. And then JJ Kevillars, it was part of the search effort for the OSIS project, which I'll mention briefly, and Anne Derbyshire, who is not part of the original work, but has been very instrumental in sort of the interpretation of this effort. So the picture that you see on the right-hand side are the binaries that have been found in our survey, and I'll go into a little bit more detail on that as we go forward. So I'm going to start off with sort of a general overview for those of you to sort of orient you in the Kuiper belt, since I'm assuming that this particular group has a combination of sort of outer solar system people, but a lot of you focus more on the ice giants rather than the small bodies. So in small body studies, we're looking specifically at dynamics. We're looking at mean motion resonances. This plot is kind of an old plot, but I really like it because it shows in inclination space and semi-major axis space the sort of the diversity of objects that we have. So the blue objects in the center here are what we would sort of refer to as the classical Kuiper belt. We divide this up sort of as a low inclination, high inclination group of objects. The objects in red are the mean motion resonances with Neptune. So this is where sort of the giant planets come in, and trying to understand the story of how they interacted with the small bodies, studying the physical properties of the small bodies in order to sort of backwards interpret what might have happened with the giant planets in terms of their migration and their interaction. You'll notice that the large circles here are all of the dwarf planets. They're all in this sort of the scattered population. Some of them are in the resonances, but the larger objects do tend to have larger inclinations. These objects also tend to have icy surfaces, as the DISCOS project has demonstrated, and among others, as well as many of them also have satellites, which will come into play later. And then we have the centaur population, which are sort of interspersed among the giant planets. And they have characteristics that are similar of the Kuiper belt objects. They also have characteristics that are similar to some of the icy moons. Anne Burbisher is the one on this sort of team who can really speak to the icy moons. So I'm not gonna delve into that too much, but she's done a lot of work sort of comparing our Kuiper belt properties with the icy moon properties of the giant planets. Excuse me. And then these gray objects, or sort of the scattered disk objects, I'm not really going to focus on that in this talk, but we are actually, as part of the New Horizons project, New Horizons is now at 61 AU, and we're still looking for another object that we could possibly fly by. We actually have found some objects that are out further, like 70 AU. I think we've got one or two that are 70, 80 AU. And we've been using Subaru. We're hoping to drill into some of the Rubin data, and hopefully Roman as well, to potentially find a flyby object. But there are other objects that are on our docket to look at as we continue through the Kuiper belt. So the sort of extended range here gets into where New Horizons is currently. And then obviously the next step, once you kind of know where the objects are, is to try to understand their physical properties. So obviously these objects are a long ways away. We can't go, sort of stick probes in them, but we can study them from what the reflected sunlight provides for us. So we have colors, which originally started out in simply the optical. My very first project was looking at some NICMA spectra that was taken with Hubble, and it was very, very low signal noise. So it's amazing to see what we've come to get with JWST these days. We've extended that to the submillimeter. The UV, Michelle has a graduate student just about finishing who's been looking at the UV properties of this particular data set, and then obviously extending into the infrared and the near infrared. We look with respect to light curves, and we now have long enough baselines on a lot of these objects that we don't just have a single light curve. We can actually construct a light curve that spans over, say, 20 years, where you can start to actually get information about the pole positions and such. I'm not going to talk about pole positions today, but it does sort of play into some of the research that we've been doing. And then Anne's work on phase angles, which again is also a long-term project, because you have to accumulate information about the phase that we can see at 0 phase angle, where we are here on the Earth. From the Earth, we're limited for Kuiper belt objects to about 2 degrees in terms of the reflectivity that we can get looking at the surface features. But from New Horizons, we've actually been able to observe a large number of objects at very high phase angles. So trying to construct that combination, and that's where that work can connect up to the icy satellites. Spectroscopy, looking for ices. Occultations, again, I'm not going to delve into that a lot, but Arakoth, we actually sort of projected that it might be binary based on an occultation observation of it. So it was really cool. We flew past it and there was a binary. But there's been a lot of work done over the years as well recently with Gaia that allows us to predict where occultations are going to happen very accurately. So I know that Anne does these observations on a regular basis from her house in Colorado, looking for shapes and sizes of Kuiper belt objects. And then direct imaging, which is kind of where I stepped in, or where I've been doing a lot of the work using Hubble. And then also, we haven't actually found a lot of binaries with JWST because we haven't done a lot of searches of that specifically, but studying them is sort of the resolved spectroscopy as much as possible. And of course, New Horizons allowed us to do some crater comparisons between Arakoth and the Pluto system, and then also looking at shape. So, didn't realize that was animated. So these are a couple older plots, but the plot on the left-hand side is a summary plot from Dave Jewett a while ago, but I really like this plot because it demonstrates the diversity of surfaces that we have. So again, we're only looking at sort of the top layers, but it really demonstrates that depending on where the object is, the transitions from what's happened from solar radiation, as well as maybe how things have migrated or been jostled around. So we're going to focus on the cold classical region here, which is this upper dot. Whoops, I guess I can't do that. Sorry. I don't know if you can see my pointer. The upper right plot corner here, the cold classical objects. But you can see that these are different from sort of the average KBOs, the hot classical KBOs, which have much more neutral colors. And then some of the other small body populations. And of course, you could do the same sort of plot looking at the asteroid population, and looking at, we're seeing different surface materials, but again, sort of being able to discern what's happened dynamically and from looking at the surfaces. Now, the DISCOS project from JWST has demonstrated that there are sort of three major surfaces that have come out. There have been some additional subtleties, but they've identified sort of this bowl feature for some of the surfaces, and their objects are, I'd say, the objects in the DISCOS project are at about their faintest objects are about sort of the largest, or a little bit sort of overlapping with the objects in our survey. So we're going fainter than them, just because from a practical perspective, spectroscopy, you can only go so far. But it's just interesting to see how to try to figure out how the spectrum matches up with the colors. So we've got the bowl objects with the water ice feature, the cliff objects where you've got sort of this stretch here, the methane features, and then the CO2 fundamental feature, and then the double dip where you've got sort of this double lip here with both the water ice as well as the CO2 fundamental. And so there's been a lot of work done. There's also been a lot of laboratory work recently to try to understand what's happening physically on these surfaces. So we're using these as traces of migration and then relationships of the small bodies to each other. Some work that our group has been working on for a long time, which has been led by Wes Frazier from our Outer Solar System project, and I'll get into the details of that in just a couple slides. I guess I should have put that further up. But we've looked at, we had two concurrent projects. We were looking with Gemini in the optical, and then also using CFHT and picking up colors in the UV, and then getting some colors in the J filter. So it's sort of trying to span the full gamut. The takeaway from this is basically that we think that there are sort of, you can duplicate the colors if you assume basically two different types of surfaces for objects, and you can mix them among a faint sort of a bright IR color and a faint IR surface. So that maps, so that's what these two colors are. So we've got the blue and the red, and then this is the reddening line, which is sort of a reference point that we use for Kuiper belt studies. And so you can see that you can map. So this is, sorry, I have a hard time. I wear progressive lenses. R minus J, and then R minus Z and U minus G connected to the G minus R, which is sort of more the visible color that we tend to think about. And so trying to understand sort of the sizes of the bodies, how they map out with color, as well as location and shape. Another approach to this is also looking not for the colors, but is looking at the light curves to try to understand the physical properties. This is a very old plot from Scott Shepard, but just the idea that initially when we were looking at these objects, we're just looking at how they rotate and thinking that objects that were more elongated might be binary, identifying some of these as binary. These are actually binary asteroids. And then elongated, maybe, specifically binary, and then specifically rotationally elongated. Now, some of the longer rotation periods we found actually are more likely to be binary. The tidal interactions have drawn out the rotational period. So this was sort of an early approach at trying to understand the light curves, and we've made that much more sophisticated over the years. So one of the things that we've looked at a lot, given the Arrokoth observations, as well as looking for additional binaries, is to think about how the light curves influence or how the binaries influence the light curve shape that we see. And so this is just sort of a schematic. This is from work I did with Mark Showalter a number of years ago, that if you have two objects that are the same size, depending on how far separated they are, you either end up with resolved light curves, you might end up with them sort of connected like we have with Arrokoth, or if you have a secondary that's much smaller, right, then it's going to be dominated by the light curve of the primary. But when you get these binaries, you also get this diagnostic sort of V shape as the objects go back and forth relative to each other, so passing in front of each other when you have a mutual event. So this is sort of one way of looking at it. Another way is that this is if you have the contact spheres, what you end up with respect to the light curve amplitudes, and then the equivalent ellipsoids. So depending on how what the shape is, how you interpret that. And that played in a lot as our interpretation for Arakoth. So we discovered Arakoth with Hubble, 26.5 magnitude object. And I went after it with HST to try to get a light curve. And I basically had a flat light curve, which was sort of frustrating. We couldn't say a whole lot about the object other than we knew that it was red. It matched up with the colors of the cold classical objects, which is the area dynamically where it resided. But we're trying to think about different ways that we might interpret the light curve or not see a light curve. And Mark Bowie led an effort to get an occultation of Arakoth. And that occultation suggested actually this sort of binary format. So flying towards the object, when we got there, of course, we found that it was a binary, a contact binary. And so what you see is that above this particular, in this gray area, because of the angle of approach, we're looking straight down the pole, which meant that we really weren't seeing much of the rotation. And so obviously, if you look at it from a different perspective, which is where the phase angle work comes in, that gives you an opportunity to see the object not just from one particular perspective, but from the broader perspective. So you need a combination of information as you're trying to interpret these objects. It's not just a single point and shoot. You actually want to accrete data over a period of years to sort of get the full picture for any of these objects. And in terms of the phase angles, this is not my bread and butter, so I'm not going to try to go into a lot of detail with this. But this is some work that Anne has done with our New Horizons efforts. And basically what you see here is that depending on the different types of objects and the types of surfaces, that you get different reflectivity with respect to the phase angle. So whether you're having ice that's shining back or whether you have sort of a rougher surface. All of the objects over here on the left-hand side are icy objects. When you get to the cold classicals, obviously the DISCOS program has showed us that there are plenty of ices on these surfaces, but their reflectivities are much different. So the surfaces of the smaller KBOs have more backscattering than those of the dwarf planets. So this is a sort of a different approach to looking at this. And so we have sort of a smoother surface and a rougher surface. All of the what we call DKBOs, distant KBOs, fall along sort of more the smoother surface here, so higher backscattering. Okay, and then obviously our last, our favorite opportunity is when we actually get to take direct images. We've tried to do that as much as we can with Hubble. We don't get the surfaces, we just get point sources. These are just some images that I correlated for our New Horizons for our Pluto conference that's coming up at APL in just under a month. So these are from the New Horizons mission, but you can see the different shapes that we get. These are the satellites of Pluto, obviously large objects, Charon, and Arakoth. And obviously Arakoth is like 20, 25 kilometers, whereas Pluto is very large. Some of these other satellites, Nix and Hydra, Styx and Kerberos are much closer in size. Kerberos and Styx in particular are much closer in size to Arakoth. And so the last idea is, again, to look at some of these and some of the cratering population statistics and the types of craters, that sort of the lumpy surface that we've tried to interpret in a physical sense. So that's sort of an overview, again, just to sort of ground us in what we're thinking about in terms of the Kuiper belt. We focused on binaries, or I've focused on binaries, because it allows us as much as possible to get a sort of a more physical approach to what's happening, right? So if you have a system mass, which you can get through measuring the orbit of the object, the semi-major axis, and a period, then you can make some assumptions either about the albedo or about the density and try to understand something about the actual physical composition of the object, or how much void space it might have in it, how it's going to interact with the other objects. This is a sort of a sample from different interpretations of Pluto in the past. So this is sort of the driver for binaries, is that a single object, you just get the surface, you just get the dynamical information, and you can compare it with other singles. But with the binaries, you can actually try to sort of delve deeper into the physics of the object. Okay, so for this particular project, this was done with the Hubble Space Telescope, and the questions that we were asking were, what is the underlying unbiased binary fraction in the cold classical population in particular at different resolutions and separations? We also wanted to see how the colors of the binary systems in the single object compare with each other. Some early work that I had done as a postdoc seems to suggest that the binaries the colors of the binaries are basically identical with each other. That's not quite the case, but that still seems to hold true. And then also, do the primaries and secondaries share colors for the larger dynamically homogeneous population of binary KBOs? So sort of doing comparisons between the binary population and the single population, and trying to understand whether the binaries have been around for a long time or whether sort of they're a newer addition. Whoops. Our survey selection came from the AUSSIS project. So this was the Outer Solar System Origin Survey that was led out of Canada, our group at Victoria, Canada. And so basically it was a 4-year survey. We surveyed different slices of the sky. Each one of these blue slices was a survey component, and it was observed over the course of 2 to 3 years. So all the objects were tracked with the idea that we could debias the survey because we know where we've looked and found things. We know even after trying to track them if we've lost objects. The gray boxes are the galactic plane, and so we avoided those. Now, ironically, for the New Horizons project, we've been trying to look in those regions, and we actually were looking at a different trajectory than all the other surveys because of that. And so we're finding, like I said, some more distant objects than have been found in some other surveys as a result of that, I think. So anyway, so we started with this. And so this survey observed the entire population of KBOs, so the resonance, the scattered disk, the classical, and we picked up some centaurs as well. And so then the idea was to sub-select from this just in the cold classical region, because that's where there seems to be a plethora of binaries, to get colors for those objects and just sort of study that particular group. So this is, if you look at H magnitude space, the little box or the sort of little cluster of objects you see is what we commonly called the core of the Kuiper belt, of the cold Kuiper belt region, that we think is sort of a region that's dynamically been there for a long time. It maybe got pushed out as the giant planets migrated, but we think that that population might be primordial for a number of different reasons. We use the wide field camera 3 on Hubble with the UVIS filters, the F606W and the F814, which is kind of similar to a V-I. We looked at 198 cold classical KBOs. I think one of those we lost, but everything else is been analyzed. And we were looking for a combination of color information and binary information. As I said in previous studies, so this was my original work from 2009, where we found that the primary and secondary objects were correlated, and that they're indistinguishable from the background population. So their colors as a whole represent the larger population of KBOs, but individually their colors are correlated with each other. So whatever mechanism is coloring the primary or the binaries and the singles is consistent. The implication for that is that the binaries are primordial and indicative of their origin as part of a locally homogeneous, globally heterogeneous population, because the colors of KBOs are different depending on where they're located in the belt. The caveats are that some fraction of the singles might be unresolved binaries, and not all of the objects are from the same dynamic class in the original work. And so that was kind of what we were trying to address with some of the Colossus and Solus project. And then Michael Marset in 2020 looked specifically in the infrared, and he looked at 3 objects in particular with these measurements. It was a small sample, but basically it gave a similar result. So this is the sample of the data. This is what a single object looks like. So you're seeing on the upper left-hand side the data, and then a Tiny Tim model and 2 residuals on the bottom for a single, and then binaries separated with different resolutions. So obviously, the ones that are really clearly binary, it's real easy to do resolve photometry for that. We have a PSF fitting using Tiny Tim, where we basically overlap the PSFs and do an optimization so that we can get the individual colors for each object. So that allows us to sort of deal with the overlapping wings. We get the uncertainty from the scatter and the formal propagation of the errors. So the closer the objects there are, the larger the photometric uncertainties, because the fits are more variable, but we get some good consistent results because there's 4 observations that go into each solution. Okay, so when we then plot up the results, this is plotting the color versus the H magnitude. Not, you're going to see a bunch of plots, and they're all sort of taking the same data set and trying to slice and dice it in different ways to try to interpret it in a physical sense. So there are 23 clearly resolved binary systems. The H magnitude average of that is 6.5 or 6.6 rather. And Simon Porter took the algorithms that we were using and sort of I guess I'd say improved them, and ran through the whole system and looked for what we would call sort of blended binaries. So not being able to do the resolved photometry, but identifying them as blended systems. So trying to get at sort of what are the colors of sort of the singles, what are the colors of the resolved objects, and then can you say anything about sort of that transition region? He identified 19 of these blended binary systems. Some of those I had actually identified sort of as maybe resolved binaries, so that's sort of a separate subset, but those all have separations smaller than 0.05 arc seconds. And again, it's a projected separation, right? So because we're looking at the co-classical population, they're about all the same heliocentric distance, heliocentric geocentric distance, but still sort of paying attention to that. So I've plotted things with respect to hill sphere later to sort of get at that sense of it. And so they have a magnitude average of about 6.9. They tend to be a little bit fainter objects. And then all of the singles that we observed are apparent signals. So they're singles as far as we can identify them, go even to smaller sizes, so 7.6. So the binary systems on average that we looked at are 1 magnitude brighter than solitary objects in terms of the ones that we can identify specifically as resolved. And the blended objects are kind of in the middle. And I think that's consistent with the fact that, you're trending towards, if a blended object, you observe it at the point where, you don't quite see the extra component, then it's going to look like a single. And so that has some implications for sort of the colors based on the colors of the two components as well. Looking at the resolved objects in terms of delta magnitude, because that also can be a factor, right? So if you combine the color and you have sort of a small secondary and a large primary, then of course your secondary is not contributing very much. So something like Iris, which has a very small moon, if you include the moon in Iris's color observation or brightness color observation, it's not a very strong contributor. So it's fairly consistent that we have all of these are sort of within 1 magnitude. So they're not quite equal size binaries, but they're fairly close. And then a couple that were sort of more lopsided. There were a couple objects in our survey that had been previously observed to be widely separated binaries, but they were within that whole classical. They were within our original survey, and they were also within the population as we subselected. So we included them, and it gave us a cross correlation as well to other studies that have been done. And so this is effectively the V and the I, and again, not many significant differences in the secondaries based on the identification of binaries. So comparing the single, blended, and resolved binaries and their particular colors. So this is just plotted versus the F606W. This is just the native HST colors. And then for reference, Pluto, solar color, and Mars, which of course is sort of in our mind's eye very red. We can see that the apparent singles, they're solitary at the limit of the resolution that we have. The blended objects, of course, are from Simon's paper. And then the weighted means of the colors. So you can see that the means are not significantly different. The binaries they're all kind of, I would say, red objects, which is about what we would expect for the co-classical population. But you can see that there's just differences, of course, in sort of the depths that we're getting to for each of these. You can also see from this plot that the colors are sort of representative of the background population. So the singles we would say is sort of the background population. The gray objects are other colors that have been measured with Hubble in these same filters, primarily by some work done by Wes Frazier and his collaborators at the time. And so they're still representative of that background population. So whatever is coloring the binaries, if they're different, has to be happening sort of maybe within the systems rather than external to the systems, because they're still representative of that broader sample. If we do a chaos test, this is uncorrected for the size dependency, we see that there's sort of this tail in the singles, in the red, and the singles being very red. And these are also looking at sort of, I will show you another plot that shows it sort of correlated with size. We have the blended objects, which is this green curve, and then the binaries. So the means of the color distributions of the solitary and the binary objects is similar. The red tail is present in the solitary objects, and it doesn't really appear in the binaries. And so that tells us there's something sort of physically different. Now, again, we need to think about sort of sample size and identification of what the binaries are. If we plot just the resolved colors, so this is just looking at the binaries, those 23 objects, the pink points are the objects from our survey. The green points are objects from my previous work. The 2 points down at the end here, I've adapted from work by others. And the gray dots are objects that are not classical objects, not cold classicals. And so what you see in this dashed line in the middle that goes from the top to the bottom is just a one-to-one correlation. So if it was a perfect one-to-one correlation, you would see everything clustered around there. These are linear fits to the different groups. So the pink line is just to the Colossus data set. And so here you see that the secondaries are, sloped different from that, about half a couple tenths of a magnitude different. The dashed line in the gray, again, it's moving closer to that one-to-one correlation. But the takeaway here is there's still a linear relationship, but the secondaries appear to be systematically redder. And if we just look at these colors, for the primaries, the average is 0.963 and the secondary is 0.994. It's not a significant difference, but it's enough of a difference to sort of try to think about, is there something going on within the system? Using a chaos test, the components look similar. The secondaries are statistically inconsistent with being drawn from the same parent population as the primaries. They're redder. If we fit a line to the color brightness trend, we notice in the full sample, we get a slope of 0.06 magnitudes. If you take any delta magnitude in the given system and correct for the size dependence, so again, thinking about the fact that the secondaries are always smaller, the colors in the primaries do become compatible. So if it's just a size transition statistically, then they're still basically the same. I also plotted this thinking about, again, using H magnitude as a proxy for size and comparing these. So the secondaries are systematically different in their slope with respect to size. The blended are most like the primaries. There's a trend of the smaller objects being redder in both of the populations. Of course, we're only measuring so in the binary systems, the smaller objects are redder, which would be consistent with looking at all of the singles and the fainter objects also being redder. So that sort of compares. The very small objects dominate the color distribution of the solitaries, where the larger, less red objects dominate the color distribution of the binaries. And so again, the green is the blended, the black is the primary, sorry, the primaries, the primaries. The pink is the resolved individual colors combined as a color, color combined at the end. And then the orange is the secondaries by themselves. And the blue one here is actually just the secondary, just the singles. So the singles are sort of in the middle. Alan Stern proposed this idea of ejecta exchange for the Pluto system in particular. So the idea is that if you have two objects that are orbiting each other, if you micrometeorite impact the surface of one, that the material that you eject off the surface of one could re-impact on the surface of another. The larger object obviously has a larger gravity, so you can move material from the secondary to the primary, not so easily from the primary to the secondary. Although we know that in the Pluto system, Sharon has a sort of a red pole, and it's not unlikely that some of that material could have come from Pluto. So what I did here is I plotted the hill radius, I calculated the hill radius, and then I plotted the separation and the fraction of the hill radius that separation is, how far it is out. And plotted that versus an H magnitude that's simply calculated from the data. And then here you see the color again. So in this particular plot, I did this with a different program, so I apologize, the colors don't match. The primary is blue and the secondary is orange. So you can see again, the smaller objects are the secondaries, and there's a trend here as you move further out. You actually see, actually this is one I want to see, you actually see the color switch. So the further out objects, the primary is actually redder than the secondary, which is sort of an interesting, it sort of makes that transition sort of around sort of 0.8 or 1 of the Hill radius. So that may have some impact in terms of how we would interpret the physical processes happening here. The smaller separations are obviously easier for painting. So if your micrometeorite impacts something off of one, it's easier to paint that if you're much closer in the Hill sphere than you are further out. And I think that is consistent with that interpretation. There have been a number of formation models proposed for binaries in the Kuiper belt over the years, anywhere from physical collisions to sort of an energy exchange where you have objects that are close to each other with smaller objects that take away energy to allow you to capture in a binary system. The energy exchange method doesn't do a good job of explaining why the colors would be the same or why you've got different colors within the binary systems themselves. And then this idea recently, and I'd say probably in the last 5 to 10 years, of gravitational collapse and the streaming instability are sort of the model that we're testing now. And so here you have binaries forming within the solar nebula where they are getting pushed out by the giant planets as the giant planets move and interact with them. But you actually do have a consistency here for both the size. I didn't include anything here in terms of the pole positions, but it's consistent with prograde rotation, which is one thing that we've observed. Will Grande has led that effort, as well as being able to have sort of objects that are similar colored in general to the general population, but also unique in their particular locations. And these are the references for all of those. At one point I did an interesting sort of diagram, and so I included this sort of last minute this morning, but I thought it might be instructive as a flow chart. So if we have comparison of the binaries with the singles, if they have the same color composition versus if they have different color compositions. So we would say that these objects have the same color composition in general as the singles. So the different ways that you might interpret that, different things that might be happening, surface weathering that affects all the objects the same in the different heliocentric distances. The formation mechanism is not influencing the color or the composition. Formation in the homogeneous disk. Sorry, my little zoom window is right on top of that line. And so this is all consistent with the gravitational collapse, streaming instability formation mechanism. If we compare the binary components, we see some difference in the color. The composition so far, there's only been a couple measurements with JWST for resolve spectroscopy, and so far the composition has been the same. But it might be size dependent, and we might be having sort of some exchange between the primary and secondary surfaces in terms of the material. So in summary, 23 of our 197 objects are well-resolved binaries. That's a binary fraction of about 12% at face value, 21% with blended objects included. The light curve measurements that Audrey Thurin and Scott Shepard have been working on seem to imply throughout the Kuiper belt that the binary population is high. But in the cold classical region in particular, their studies with looking at contact binaries in particular, their suggestion is, or their measurements suggest something as many as like 40 or 50%. So this is consistent with observations that have been made through other studies as well. The binary systems are on average 1 magnitude brighter than the solitary objects. The secondaries are systematically redder than the primaries. The blended objects are consistent with the binary sample. And the very small objects dominate the color distribution of the solitaries, but the larger, less red objects dominate the color distribution of the binaries. So our thought is that whatever's going on with color versus size is probably about the size at formation, and not due to just the fragmentation in those objects being read, or that there's something going on inside the binary system. And obviously, looking at Arakoth as a specific example of a contact binary, the two lobes are basically the same color with each other. So, there's, and based on it being a representative of sort of the larger population of contact binaries, whatever is causing that system to happen is sort of a slow process rather than a collision process. Both the optical and infrared colors support the notion that cold classical objects come from a different distribution than the resonant or excited scattered objects. That's not really from this particular study, but that's one thing that has been picked up from the past. The colors of the equal size binaries are mostly consistent with each other, but the primaries, so actually I should say the secondaries are redder. The colors of the equal size binaries, yes, are representative of the regions within which they reside, especially in the cold classical region. And so the conclusion, I think, still stands that the binaries form from a homogeneous within their dynamical locations in a moderately inhomogeneous disk, and that the gravitational collapse streaming instability is consistent with the results that we see. This is sort of a schematic that came out of some work that Michelle Bannister and Meg Schwam did, that sort of spearheaded sort of the deeper dive into the binaries and the cold classicals. That sort of, you can have sort of maybe different types or different groupings of material at different locations, and as the giant planets are interacting and migrating, that this is sort of tracking, or that allows us to track where these particular objects end up. That allows us to track what's happening in a dynamical sense. So thanks for listening. I'm happy to take questions. And hopefully this paper will be submitted very shortly.
All right, thank you so much. Let's put our clap reactions in. Well, yeah, this is so interesting. If you have questions, please feel free to put them in the chat or raise your hand, and I'll call on your name. We already have a question in the chat, but I'm going to steal the first question. I'm wondering if you can speak to how the work that you've done can contribute to our understanding of captured Kuiper belt objects like Triton that we see in Neptune.
So I know that there was a paper written sometime in the last couple of years, and I did not read it, so I can't comment on it. At one point, I know that Triton, one of the models for Triton was the question of whether it was originally a binary object and was captured and lost one of its components. I don't know whether that still stands either dynamically or, in terms of that research, but I know that is one thing that has been considered for Triton, based on a variety of properties. Triton is very similar to Pluto in many cases. So, studies of Pluto, maybe and again, I don't study Triton specifically, but my guess is that there are studies of Pluto that can contribute to understanding Triton a lot more as well. I think it's interesting personally. So one of the comments that I heard a lot from the New Horizons flyby of Pluto is, oh, the surface looks so young. And that was one thing when I was growing up. Voyager was flying through and looking at Triton's surface with the geysers and such. So just it struck me that both Triton and Pluto have sort of relatively young looking surfaces, where in the outer solar system you really wouldn't expect that per se. So I know there's been interesting work where people have tried to sort of explain how you could get that sort of surface, and some really interesting geological studies that have been sort of proposed for heating in that region of the belt. But I'm afraid that's not my work at all.
Okay, thank you.
We have a
question from
if we head out to the hard button, grab a bunch of mass, move it around, prepare the mass station, cause other. Okay, I'm not quite sure that I understand Terry's question.
Terry, do you want to unmute and clarify a little bit?
Yeah, happy to chat that out. Absolutely. First of all, amazing talk, brilliant. I can't believe you've spent this much time studying this information. That's really, I can't even quantify the value of it. Rebalancing. So paper out, Harrison et al., not published, so it's pre-published. came up with some pretty interesting conclusions with respect to mining, and they were working in the asteroid belts, working and then moving out to the Kuiper. And I'm like, I don't think we should be moving those things around. Before you know it, it's a mass of billiard balls, and that's my opinion. But there you are. That was the reason for the question.
Okay, I don't know. So I don't do orbital dynamics, but I think it would be really hard to move objects physically if that's what you're asking about in physical space. I mean, like, I know that the idea of asteroid mining, of using resources and I guess bringing them back to the Earth, um,
Or a stable orbit, yes.
or a
Yeah.
stable orbit, but like, I mean, the Kuiper Belt is just the amount of energy that you would need. Like, so it's taken us, we launched New Horizons in 2006. It took us in 2000 till 2009, sorry, 2014 to get out there, 15. And that was with the Jupiter flyby, right? So just the energy, we're to get to the Kuiper Belt is huge. So,
Oh.
Yeah.
Yeah, they would. I've always thought that as well. And where were they going to get the Delta V to make all of those maneuvers out there? And maybe they're harvesting helium out of the Saturn's atmosphere. That's the new
I mean,
thing
if you're
I
doing
heard.
something like that, I would think comets would be a much better resource,
Cool.
because they're already
Very-
coming towards the sun. So,
Absolutely. Well said. Good point. All right.
so
Excellent thought. You're
let's see.
amazing.
Are the ices in the Kuiper only water methane? No. So there is CO2, there's carbon monoxide. We've actually, I don't know if I have it in this slide, in the slide I showed you before from the DISCOS program, they've found some amazingly interesting things on the surfaces of these objects. This is just a sample, but there's a paper that just came out by Brunetto et al. It's 2005. I just found it the other day. But they have basically a huge plot that shows the DISCOS objects sorted by these different designations. So the cliff, the double dip, and the bowl, subdividing by resonance and full classical and such, and then the mapped out with the laboratory ices. So just, I guess I'd encourage you to look at that particular paper because that would give you a lot more detail. But yes, there's a lot of stuff going on out in the Kuiper Belt beyond what we had ever sort of guessed. We've even found, very, very low signal, but I actually think that there's slight methane in the air cloud spectrum. So, there's a lot of stuff, a lot of ices that we had not really anticipated necessarily at this point.
Okay, Matthew, I
Let's
see you have your
Best
hand up.
guess on the origin of Pluto components. Yeah, so for the longest time, there's been a lot of discussion. Sorry, I'm just reading through the chat, so I'll go back. For the Pluto system, there was a lot of discussion for a long time about it being a collisional system. I think there are some new models out that suggest that you could get Pluto and its moons without it actually being a collision. I think Pluto and Charon is more likely a collision, but I think that you can actually get the smaller moons without necessarily invoking that. Okay, somebody had a hand. Sorry, Matthew, go ahead. Oh,
yeah, I put my question in chat, but could you just help me here and give me
Yes.
sort of an intuition on what your colors actually mean? Because I always think of, cold classicals as the very red population of the Kuiper Belt, and you're saying that some are bluer, some are redder. What's the sort of
yeah.
dividing line?
So let me put this plot up. So this is basically like a V minus I color.
Okay.
So Pluto is, well, solar color is down here, so kind of neutral. So we're talking about objects that are redder than the sun, but not as red as, say, Mars or Pholus is sort of has always been sort of our poster child for a red sloped object. It's a centaur, but it's sort of in that bracket. Does that help?
Yeah, I was asking even more specifically the typical
Okay.
red, very red dichotomy that we have. What color is that for your Hubble filters? Is that around 0.9-ish or?
Oh, yes. Okay. How does that translate? So for sorry, the delta magnitude is I think 0.15 when I do the color correlation. I have a whole bunch of tables, and I what I've done is I've used the Hubble SynFote. So basically, one of the things that is difficult about this, of course, is that to translate between all the filter correlations. But anyway, yeah, so I think it's a difference of like 0.15 magnitudes, and I think it's up. So I think it's my color plus 0.15.
Okay.
I should, you're right. I should include that. And actually, if you look at my 2009 paper, you'll see it plotted with both.
Yeah.
And when this gets published, I will have both of them. If it had an easy way of getting to the table that it's in, I could tell you real quick, but
Yeah.
send me an
I tend to
email and
like
I can tell you
spectral
what that is.
slopes because they make it so that you don't have to have like a reference set of colors.
Yes. So the spectral slope for this is about 20.
Okay. Okay.
Yeah.
Thank you.
Yep. Okay. Oh, let's see.
So Michael is asking, how does this work support, refute, etc., the very red work of Brown, Wong, and I guess Michael's lab experiments?
Yeah, so I'm not so familiar with the lab experiments, but I would say this is consistent with their results and their interpretations.
Okay. Well, if you are hanging on to a question you want to get out there, feel free to put it into the chat. And at this point, we'll transition to Jody to give us a little bit of a community update, but still put those questions in the chat if you still have them. So go ahead, Jody.
Sure. Yeah. And Susan, really excellent talk. That was fantastic. Yeah. So I will real quick share the community news slides. Let's see. There we go. Yeah. So for folks who maybe haven't seen or are new, we like to have this up at the end of every Ice Giant System seminar series talk, just to sort of keep the community cohesive and together and staying informed on what's going on in all of our lives. So and what I'm going to do is I'm going to copy paste this into the chat so that you can click on the links if it will let me copy paste it. I hope that it does. It doesn't. Let me do a little bit at a time. Maybe that will work. Yeah. Okay, cool. Alrighty, so coming up next month, we've got another version, another iteration of the Ice Giant System seminar series. We've got Dr. Dolan Bhattacharya from CU Boulder giving a talk. And then this just came in my inbox recently. There's a NASA SMD budget virtual community meeting coming up in just a couple days on Thursday. And then for folks
there is a Slido link if you need to put, or you would like to put some questions in. I can see
yes, great point. Great. Yeah, if you can, yeah, that'd be awesome. Yeah, thank you. Right, and then for those of you that are looking for postdocs or new opportunities, there is a postdoc position available for cloud formation modeling, which might be particularly relevant to some folks in the Ice Giants community. So I wanted to just plug that. And then there's a Habitable Worlds Observatory science cases that are open for comments and suggestions and feedback. And then the last 2 points here are things that we've had on previous community news slides. There's a Uranus rings and small moons working group that Matt Hedman and Tracy Becker are involved in. And so if you're interested in joining that, just email them to get onto their little mailing list there. And then there's also this community sourced Google Docs of people that are looking for PhD students, and then also people that are going to be PhD students looking for opportunities. So those are those 2 links there. Oh, did you find? Yes, awesome, great. You found the link to post questions for that SMD meeting. Awesome. But I think that's all I've got for community news. And of course, if anyone has anything that they'd like to plug, or maybe a position or a meeting that you're interested in getting the word out about, definitely let us know. We can always include it in the listserv emails that go out to help advertise this series. And I can also put it inside this slide for the community news whenever we do them at the end of the seminars. So
Can I
back
pop
to
in
you.
real quick here?
Of course, yes, please.
For anybody who's actually physically at APL, the Pluto Plus 10 conference
right.
is happening next month. And the 16th is our public event night. So if you're around and you want to come visit with people or whatever, at 6 p.m. on Wednesday night in the Kirchhoff's, I can never say it right. The auditorium there,
Coffee Center.
Coffee
Center.
Center, yeah.
yes, feel free to come and you can interact with the scientists there.
Awesome. Yeah, thank you for that plug. Is there, do you know if there's a link to register
There's
either
no
virtually or in
there's
person?
no registration. There's no registration.
Okay.
I mean, the
Awesome.
the meeting itself happens for the week, and that it's a paid meeting, but the public event is completely open.
Okay.
There's no
Okay.
there's no RSVP, no nothing. Just show up. It's light refreshments. It's geared towards the public, so it's we're gonna have like popcorn and ice cream and stuff like that for the kids, and sort of a panel discussion and such. But it's it's just open for anybody.
Awesome. Oh, well, I will be there then. That's right down the road from me. Yeah, thanks, Perry, for putting the link into the chat.
All right. Well, I don't see any more questions for Susan in the chat. So thank you so much again for giving this wonderful presentation. Thank you all for attending. And everyone have a great rest of your week. Take care.
Thanks, everyone.
Bye.